Okay, right. I suppose really. I mean, I've covered NMR. I've done all that. I've covered most of the stuff really, and this, I suppose, dare I say, is pretty much the last thing. Everything else, no, there's nothing else. We've reached the end. I reckon. Okay, so the end. This actually comes before NMR, but I decided to get NMR out of the way because it's such a big deal. This is chromatography, and you might find some questions on chromatography which you've got to watch. So we'll have a quick look at chromatography just so you got some idea. Two types. First type is called thin layer chromatography. TLC. Okay, won't take me long to teach this, it's hardly complicated. Right, you've got a stationary phase. Right, and that's fixed in place, as the word suggests, it doesn't move. And it basically absorbs the components. The stationary phase in thin layer chromatography is probably paper, okay, filter paper. And you've got a mobile phase. Okay, which moves up the plate, carries the components. Because it's used for separating mixtures, carries the components, right? Different distances, okay? So this is just ran up the paper, All right. So then you've got something weird called an RF value, okay? It's basically this distance. All this will moved by solvent, by component, divided by distance moved by solvent front. So the premise of thin layer chromatography is basically this: different components travel different distances. So you put a blob of a mixture like ink. Ink is made up of maybe different components, different dyes, different colours. They will have different levels of solubility. They will be pulled up the stationary phase by the solvent, and if they're strongly attracted to the mobile phase by the solvent, they'll be pulled all the way to the top, or until, okay? But if they are weakly attracted to the mobile solvent, then they will only go up a small amount. So each component has a different attraction to the mobile phase and the stationary phase, because they work together, separating them out as they climb up the chromatography paper. It's as simple as that, okay? So here we are. If you look at the exam questions, you've nothing to fear. There was one on 2019 which was quite good. But have a look if you fancy it. They're straightforward, okay? You know, you take a piece of paper. I'd have done this experiment with you, but obviously, right, put it in a beaker, okay, of a solvent. Right, you put a pencil line there. Okay, it must be a line made out of something that doesn't interfere with anything. You put a pencil line there, and you put your dot of, say, black ink there. Okay, like the black ink right there. Then you put it in a solvent like that. Water is a common one, but you can use any one you like, and the solvent will travel up, and it will carry the different components contained within this black ink different distances up the paper, okay, according to how strongly each component is attracted to the water, the mobile phase, the water, if you will, or the stationary phase, separating them out. Okay, normally I'd do this with a number of colours, but let's say use a bit of imagination. All right, dot there. Imagine the solvent's carried up. Leaves me with a dot there, green, right? Dot there, red. Dot there, blue. And the solvent travels all the way to there. Okay, right, now RF values for those. RF, so that's got 3 different components in it. Okay, this black ink. RF, right? Right, well, let's say that the distance that the solvent has travelled up here, for argument's sake, is, I don't know, 9.6 centimetres. Right, so the RF value for the dot that is green, okay, RF for the dot that is red, RF for the dot that is blue. Okay, green through the middle. Measure that distance. You'll see these questions, it's no big deal. Let's say that it has travelled up from the centre of the dot to the bottom to the pencil line. That is where you measure it from. That's your baseline at the bottom. Let's say that it's 1.8 centimetres, shall we? So RF value for that is 1.8 divided by 9.6 equals, right, red one. Let's say that that has travelled up 3.9 centimetres. Okay, RF value for that is 3.9 over 9.6 equals, and the blue, let's say that that's gone up 8.7 centimetres. So RF value for that is 8.7 divided by 9.6 equals. Now, that's not the whole story. Look at a few, if you're bothered, look at a few past paper things on that. There was one last year, they dotted around and they might ask, you know, a bit more sophisticated than that, but it's not like a particularly big deal. Just look at a couple of 3 questions and you'll be absolutely fine. Okay, so that's thin layer chromatography. Fairly quick, to be honest, but you know, right, it's hardly rocket science. And next, gas chromatography, GC. I hope my flipping tablet hasn't fallen out of juice. Or, you know, GC. Right, gas chromatography. Right, okay. I mean, have a look in the book on this, okay? But basically, this is like a coil tube. Used a lot, this is. Okay, because it separates things out and you can actually capture each component, which you can't do on thin layer chromatography. Okay, normally coiled tube, it's very, this technique is coated with a solid or a liquid. Right, you can change the solid or the liquid. Okay, and that I suppose is your stationary phase. You see them everywhere. This is a perfunctory look at it really, but you know what? Then, so that's your stationary phase, and then you have an inert carrier gas, which is your mobile phase. Okay, often helium or nitrogen, right? That's your mobile phase, right? So what do? You take your mixture, you inject it in, and it goes through the coil. Now, depending on each particular component of that mixture, the way it interacts with the solid, it's much more sophisticated, or the liquid phase. How much it bonds to it will slow it down differently. Okay, so something that is injected that sticks to the stationary phase takes a long time to go through the column because it gets stuck in there. Something that doesn't interact with this solid liquid stationary phase will pass through the column very, very quickly, and in the interaction between each component and this solid liquid phase separates them out. Okay, separates them, so separation to, and also you can use it often for identification. In fact, GC is normally hooked up, is very powerful, because you can take a mixture, you can put it in the machine, it separates them out, right, and then it's attached to another machine which might analyse them, such as NMR or mass spec, which is what might analyse what each component is. Very powerful, you see it everywhere. So right, so the retention time is how long it takes from when it's injected into the column to how long it takes to pop out the other end. All right, and what it comes down to is this: similar compounds of similar molecular mass and similar, it's what you would expect, functional groups have similar retention times. So if you've got a mixture of esters, they're all going to, and that are similar relative mass, they're all going to come out at the same time. If you've got a mixture and there's two esters and one alkane, the two esters are going to be, perhaps they might come out first and the alkane come out last, or perhaps the alkane comes out first, depending what you use for your solid, and the esters come out last, okay, depending what you use for your solid liquid stationary phase. But either way, they'll be split on that basis. So you sort of, yeah, you end up with you wait, and then in your little mixture, and then you might get, oh, this has come out, oh, this has come out. It's separating them out. So the retention time, this has come out, okay, like that. There's your RT, your retention time, okay, and I think this is absorption here. So what could these be? Right, well, let's say first one that well, actually the first one is down this end, isn't it, really? I don't know. But let's say these two, close, right? Close retention time. Maybe one's methanol. Similar functional groups. One's ethanol. Here, a bit later on, maybe one of these, maybe these are aldehydes. One's ethanol, and one is propanol. That's it. That's how basically how gas chromatography works. Very, very quick overview, nothing more than that. By all means, have a bit of a look, but it does finish the spec. Okay, so well done, guys, if you've made it this far. And, you know, look after yourselves, all right? And I'll see you later.